Hello, everyone. Thank you so much for joining us today. So my name's Anthony. I am a principal at Priopta. So we focus on doing whole building life cycle assessments on typically new construction projects. So we work with design teams to reduce embodied carbon, and we also do some policy related work too. So this is an example with the BC provincial government. I really want to acknowledge the provincial government for being so forward thinking to commission this study and to explore best practices and how can we actually address embodied carbon at the provincial scale. So without further ado, this will be a very information-packed presentation, but the slides will be made available later on. So I encourage you to dig into the resources later on afterwards. First, so this is an outline of the presentation. I'm going to be covering why BC needs embodied carbon policy. Why is it important? Then I'll touch on some of the embodied carbon benchmarks and assumptions that we used for these province-wide BC projections. So one of the core tasks of this whole study was to come up with an initial estimate as to how much embodied carbon is associated with all of the new construction projected to take place in BC, between now and 2050. And so to do that, we actually looked at some of the best available statistical benchmark studies specific to different archetypes that we're evaluating, building archetypes. And then we did a projection. So from there, using that data and the projected new construction by building archetype, we then developed our initial estimates for the total province-wide embodied carbon at various different timeframes. And then once we came up with that top line number, we then also looked at, well, how does this compare with the other emission categories in the province? So the province tracks the GHG, each year they publish their GHG inventory. So we can see how does this compare with, or the scale of these embodied carbon emissions, how does it compare with other sectors of the BC economy? And in particular, operational carbon emissions from all buildings. Then we'll dive into, okay, well, how do we actually achieve these reductions on projects? So we'll be exploring a few different whole building life cycle assessment case studies. And these are more detailed designs with Revit models. And so using these different case studies, which represent different building archetypes, we'll explore some of the reduction strategies and what type of reductions we have seen on some of these projects based on some of this early modeling. We'll touch on cost impact. Obviously, cost is an important factor on projects. So what does it cost to reduce embodied carbon? Here, what we did was just summarize the best available published information that we've seen on this topic. Granted, it's fairly limited information, but we'll touch on that point. And then we'll touch on some of the proposed percentage reduction thresholds that we proposed, which could be potentially applied to a province-wide framework, something like the BC Energy Step Code. Now, mind you, that this was just kind of a modeling exercise just to demonstrate what could these thresholds potentially look like. And it may or may not look like something like the BC Energy Step Code, or maybe there's another provincial policy mechanism that gets used. But nonetheless, we're going to talk about some of the thresholds. And then we'll talk a bit about consumption-based emissions and trade. This was a topic that was of interest to Jeremy Cardona at the province, and so at the province there, I think there is some interest in looking at what does it mean to look at consumption-based emissions, in contrast to production-based emissions, which is how we typically quantify our emissions. Right? We look at the emissions that happen within our borders, and that's what we put into our greenhouse gas inventories. Right? But when we think about embodied carbon, technically, it should also include things like imports, right? If you import steel from China or from other regions, you should quantify those emissions. So it's actually more of a consumption-based approach. So we'll touch on that. And then finally, we'll wrap up by talking a bit about forestry and biogenic carbon accounting and how different approaches on this can influence our whole building LCA calculations. And then we'll summarize all of it. So a lot to get through, but all right, so let's start off with why BC needs embodied carbon policy. I'm sure most of you are familiar at this point, but embodied carbon, when we're talking about embodied carbon, we're referring to the emissions associated with construction materials. So think of all the materials that go into a building, all of the concrete, steel, glass, insulation, all of those materials have an environmental impact. And those environmental impacts take place from cradle to grave, right? So from resource extraction, so think of mining of ores or harvesting of timber, to the transportation of those materials, to the manufacturing and processing, construction, operation, all the way to end of life. And so for each of those materials that make it into the building, we're looking from cradle to grave, from resource extraction all the way to end of life, all the emissions associated with that. So you may have seen some statistics at a global level to say, well, what is the total, how much emissions is associated with embodied carbon? Well, if you look at annual CO2, global annual CO2 emissions, about 28% of global CO2 emissions annually is associated with operational carbon. So that's to operate, to heat, to cool, and operate all the buildings on the planet, 28%. A further 11% is associated with embodied carbon. So that's the new construction and major renovations, all the materials that go into that amount of construction each year, that's associated with 11% of global emissions. But the question is, what does that look like on a provincial scale? Before I dive into that, I'll touch on why this is still important at a global level. If you actually look at the new construction that's projected to take place between now and 2050, so just over the next 3 decades, and you look at that cohort of buildings that are being built over this next 3 decades, embodied carbon is estimated to account for 49% of that total emissions, with the operational carbon emissions associated with that new building stock being 51%. Now, mind you, this is just looking at a specific time interval. We're not looking at the whole lifespan of these buildings or every building that gets built over the next 3 decades. But this has a relevance to our climate targets, because if we're going to try to achieve these different emission targets or limit global warming by 1.5 or 2 degrees Celsius by 2050 or by 2100, we need to think about when these emissions are taking place. And so embodied carbon is a big slice of that. And this is important because we're projected to double the current building stock by 2060. So think of all the buildings that currently exist on the planet. We're projected to double that amount of floor area in the next 4 decades. And so that's what this map shows over the next few decades, the scale of new construction activity projected to take place by 2030, 2040, and 2060 in North America and Europe. So you can see, in the next decade, or in this current decade, China is projected to build by far the most new construction. And then in later decades, it's going to shift to other regions like Africa and India. But in North America, we still have quite a bit of new construction here. Okay, so now let's dive into BC specific numbers. So I'm just going to cut to the chase and show you some of the numbers first, and then we'll kind of go back into how these numbers were derived. So province-wide in BC, operational carbon emissions in BC associated with all the buildings each year is 8.31 megatons of CO2 annually. Now, if we looked at embodied carbon, which, mind you, is a consumption-based approach, but it's still worthwhile to compare these metrics. If we look at embodied carbon, what I did was I actually created 2 estimates for embodied carbon. One for a base scope, which includes the structure and envelope of the building. So this is typically what we include in most of the whole building LCA studies right now, or at least it's fairly standard practice. But then it doesn't include some of the other elements of a building. So I also created something called full scope, where we look not only at the structure and envelope, but also interiors, mechanical, electrical, plumbing systems, and refrigerants. Now, mind you, these numbers there's less good data on this front. And so these are kind of relying on fairly early case studies and numbers on that front. But still, I think it's useful to try to estimate the total range, the scale of emissions. So if you just look at the base scope, operational carbon, and you've put that with embodied carbon, total is about 12.2 megatons of CO2, with about 4 megatons associated with embodied carbon. And so if you did that calculation, if you just looked at the kind of building sector related emissions and you only included the base scope, embodied carbon would be about 1/3 of the total emissions, annual emissions each year. But if we included the full scope, it would bring that number up to around a little over 7 megatons of CO2, which would be about 46% of building sector related emissions, right? We'll dive deeper into these numbers, but that's kind of the top line estimate. Now, mind you, this is looking at the how do I say it? Or one thing I wanted to share was that so this is some anonymized data that was submitted to the City of Vancouver. So as some of you may know, since 2017, the City of Vancouver has been collecting whole building life cycle assessment studies at the rezoning stage. So this is schematic design stage. And what I did was took this anonymized data and kind of graphed it so that you could see the general range of emissions. This is a box plot with this line being the median. So you can see on this left side, that's embodied carbon intensity in kilogram of CO2 equivalent per meter squared of floor area. So we're doing this for apartments, for low-rise residential, townhomes, offices. Most of our data is in the low-rise residential and apartment. And then for some of these buildings, they were also reporting their operational carbon emissions. This is, again, based on early estimates, based on their energy modeling, but you can see where those numbers fall. And this is multiplied over 60 years. So we're looking at over 60-year lifespan. And the key thing here is that, you know, in our new buildings, at least based on the early preliminary modeling, the average embodied carbon is greater than the average operational carbon emissions for these new City of Vancouver rezoning buildings over 60 years. Now, mind you, these new buildings, the reason why their operational carbon emissions is so low is that the City of Vancouver also has greenhouse gas intensity limits on the operational carbon. So we're really comparing to numbers that are already very, very low. If you look at existing buildings, these operational carbon numbers would be much higher. But for the new buildings that need to be built, given that they need to comply with that operational carbon emission GHGI intensity targets or thresholds, that's how it works out. And so that's why we really need to look at embodied carbon for these new buildings. So the City of Vancouver announced as part of its Climate Emergency Action Plan, Big Move 5. And so this was one of the 6 big moves as part of our Climate Emergency Action Plan. And that one focused on embodied carbon, which basically states that by 2030, we need to reduce the embodied carbon associated with our new construction, with our new buildings, by 40% relative to 2018 as a baseline year. So that's a very significant amount of reductions that we're targeting for all new construction. So the City of Vancouver has been definitely paving the trail forward for embodied carbon policy on this front. I think it's the first city to include embodied carbon in the building code, in the Vancouver building code, and so, or building bylaw. So the question is, what about the other BC municipalities? And so what we're seeing is that other municipalities across BC have also demonstrated interest in tackling embodied carbon. So for example, the City of Nelson has published resources on low carbon building materials as part of their low carbon homes pilot. The District of North Vancouver is exploring policies and tools and incentives for reducing emissions. I think they recently announced that they would require embodied or whole building LCAs to be done as part of their rezoning process. The City of Vancouver did some research on step code homes. UBC is developing policies and guidelines around how to address emissions for UBC projects. Metro Vancouver and the resort of the municipality of Whistler have set targets to reduce embodied emissions by 40% by 2030. And the City of Langford also introduced some low carbon concrete policy. So we're seeing a bunch of scattered efforts, great efforts happening at the local level. There's definitely demand for this. But we need a coordinated provincial policy framework that will then really support all of these municipalities. And I think BC is really well positioned to innovate on whole building LCA policy. If you actually look at in the US, where most of the embodied carbon policy landscape looks like, you'll hear a lot of talk about Buy Clean policies, you know, Buy Clean California, Buy Clean Washington, Buy Clean Oregon. And most of the policies are actually tackling embodied emissions at the individual material level. So they may select certain key materials that they're going to develop limits on or reduction requirements. So for example, steel, glass, mineral wool, concrete, et cetera. And there's a lot of power and potential with that type of policy framework. But to my understanding, right now, there's not very many policies being in the US that actually address the whole building environmental impacts, right? When you think about a whole building, there's many different materials going into the building. It's not just concrete, not just steel, not just some of these key materials. And so I think there's a lot of potential to this whole building LCA type of policy, which the City of Vancouver is pursuing. And I think BC is well positioned to innovate on this front as well. So in summary, on this section, embodied carbon is a significant source of emissions. It's estimated to be between 3.93 megatons for the base scope and 7.19 megatons for the full scope annually. So it's between a third to just under a half of building sector emissions, depending on which scope you're looking at. And I think because much of the embodied carbon happens upfront, these embodied carbon policy efforts can actually have a very significant impact on our emissions. One other thing is that embodied carbon can actually be a competitive advantage for BC and for Canadian companies by creating jobs, creating valuable expertise in an area that we see there's increasing demand globally. You know, if we actually really pioneer policy, sorry, just give me one second. I just need to close the window. There's some sirens downtown. So I think this can actually create a lot of, creating bold policy in BC can actually be a competitive advantage for many local companies. This is an area that's definitely going to be addressed in the building sector globally. And a lot of regions are actually looking to Vancouver and looking to BC for their leadership. And so this is, if this is kind of where the direction is going anyways, and something that we need to address for climate change, I think this can actually create a lot of advantages for our local companies. Okay, next up, let's talk about the benchmarks and assumptions that underlie the BC projections that I worked on. So the general approach was, we first started thinking about, what if we actually model some of these different building archetypes that are representative of the different types of buildings that are represented across the province. And we create these simplified models, and then we kind of just scale it up by the total floor area. Now, while that is a possible approach, I think it may be more accurate to actually use benchmark data, statistical benchmark data based on the data that exists out there right now. Because if we just base it on these bottom-up assumptions, it's very susceptible to the specific design choices that were made on that individual building, right? So it's kind of hard to come up with the one right exact number that is the appropriate average for, for this building archetype, for across all the wall assemblies, all the different types of concrete, et cetera. So the approach that we ended up taking was to actually look at the best available published benchmark data, kilograms of CO2 equivalent per meter squared of floor area, that are representative of some of the common building archetypes. And we looked not just at the base scope, as I mentioned earlier, but also additional scopes. And the other thing was we also tried to use our best judgment to identify the potential limitations of each of these benchmark studies. And sometimes we actually applied some multipliers based on our best judgment to kind of adjust it so that we can kind of harmonize the estimates and I guess reflect what may be the best estimates on these. So for example, some of these data points, like the City of Vancouver data set that I mentioned, that's based on rezoning data. And so that's kind of early schematic design phase where we don't have clear material quantities, or we're making lots of assumptions and we don't have information on the foundation, et cetera. So I may apply a certain multiplier on top of that to get it to a level that I think is more reflective to what we've seen in some of the more detailed studies. And in terms of the floor area projections, we actually used data from Navius. So Navius worked on the Clean BC modeling assumptions. So they did a lot of the modeling behind the Clean BC program. And within their program, they have projections for how much, single family homes, how much apartment buildings, how much, all the different building archetypes, how much it's projected to build, or how much the province is projected to build at various different timeframes. So that's what we use. Now, before I get into the benchmarks, there's different software tools that are used to look at different types of buildings, right? So generally there's the Part 9 buildings, which is kind of low-rise residential, kind of single-family type homes under 600 meters squared. And then all the other bigger buildings, Part 3 buildings. And so in the Part 3 world, we use tools that are commonly used that include Athena Impact Estimator, One-Click LCA, Tally. Some projects also use EC3 as an integration. And then there's a new tool that's being developed called TallyCat, which is not released yet. In the Part 9 world, there's Builders for Climate Action by Chris Megwood's group. And also Passive House Canada has developed the an add-on to PHPP called PH Ribbon. which is also another tool. So these different tools, the thing I want to emphasize is that there's different software, they have different features, different methodology, different assumptions, different underlying databases. And so that can also make it challenging sometimes to compare studies or benchmarks that are done across these different tools. Now, just as a refresher, this is what embodied carbon can look like over the lifespan of a building. So, between, let's say the building lasts for 60 years, these yellow bars represent the operational carbon emissions, while the red bars represent the embodied carbon. On the operational front, when we're in the design phase, we use energy modeling to quantify the impact of different design options and how we can reduce the operational carbon emissions of a building and the energy use. Whereas we use life cycle assessment to quantify embodied carbon. So upfront, before the building's occupied, there's a lot of materials that go into the structure and envelope and the core of the building. So there's a big pulse of emissions up front. Then we have replacements and maintenance, and then we have end of life at the end. And also, this is important to just kind of quickly review the life cycle stages, because this will make more sense as we talk about the different benchmarks. We have these different life cycle phases. So within a life cycle assessment, we have formal definitions for each of these life cycle stages. So we have module A, B, C, and D. A to C typically represents kind of the cradle to grave emissions. So that's kind of the main set of results we typically look at. So module A looks at all the upfront carbon, so all the emissions before the building is occupied. So for example, raw material supply, A1, transportation, A2, manufacturing and processing, A3. So A1 to A3, typically that's what manufacturers report in their EPDs or environmental product declarations. And then we also have the transportation to the construction site, A4, and then construction installation, A5. So this is module A. It's all the emissions of embodied carbon emissions before the building's occupied. Then we have the use phase, which includes use, maintenance, repair, refurbishment, replacement. Replacement is probably one of the big factors where, for example, if there's a building component that doesn't last the whole lifespan of the building, like let's say it gets replaced every 20 years, we account for that. So that's where some of the emissions come from there. And then also emissions from end of life, deconstruction, demolition, C1, C2 transportation, C3 waste processing, C4 disposal. So A to C is the main set of results that you typically see reported for whole building life cycle assessments. Sometimes you'll see data also reported on module D, which is supplementary information, looking at the benefits and loads beyond the building life cycle. So for example, is there a benefit or a load associated with reusing our materials or recovering the energy? For example, if you're incinerating some materials and there's an energy recovery there, or if you're recycling the material, these things are impacting a future product cycle, like that recycled material is going to some other future product. And so it's reducing the emissions of that. So how do you quantify those benefits? This is why we sometimes report module D, but it's kind of supplementary information, because otherwise we'd be double counting because those emission savings would also get passed on to the future product life cycle. Okay, this is I don't expect you to be able to read this, but this is actually the table showing the actual assumptions that we looked at. So we looked at a few different building archetypes based on Navius's data. So we have single family detached, single family attached, apartments, office buildings, retail food buildings, so just specific subcategory, elementary and secondary schools, warehouses, and other building shells. So for each of these categories, we have floor area projections. And so what I did was actually try to come up with the best estimate based on the best benchmark data that I could find. And sometimes I also included some multipliers, as I mentioned earlier, to adjust it to what I thought would potentially be a good threshold for that. This is for the structure and envelope. So this kind of yellow column is the assumptions that we used for the module A to C emissions, whole building LCA emissions for the structure and envelope across all the archetypes. And I have text here describing the thinking behind the assumptions. And then I also looked at interiors, mechanical, electrical, plumbing, and refrigerant leakage. And so I also kind of explored some of these, came up with numbers for each one of these categories for each archetype. And again, we have assumptions listed here below. And I just want to emphasize these numbers, there's not a lot of great data on this. So think of this as kind of very early preliminary estimates. It could go up or down, but this is kind of the best that I could do with the data that I found. So next, what I'm going to do is actually just quickly skim through some of the studies, the benchmarking studies that we're citing in this, and then we'll get into the projections. So for example, for the low-rise residential sector, there's been a great study done by Builders for Climate Action using the BEAM tool. And with that tool, they did a study with Natural Resources Canada, and they did they modeled various different building types, kind of low-rise residential building types, and they had high, medium, best available, et cetera. So I kind of picked a number here. So for example, in this case, the mid-range tier 4 kilogram of CO2 per meter squared. So we looked at that. The city of Nelson also had a study, also using the BEAM tool done by the Builders for Climate Action group as well. And in that, across that sample set of, I think it was 34 homes, the mean was around 150 kilograms of CO2 per meter squared. Now, mind you, the BEAM tool only has module A1 to A3. So it doesn't have the other life cycle stages. It doesn't have replacements, doesn't have end of life. So it's not technically a whole building LCA number. And so to adjust for that, we applied some multipliers to kind of adjust it to what may be a more reasonable A to C number so that it's comparable with the other tools, the estimates. This was a study done by the city of Richmond, where they looked at a single family home in Richmond, and they looked across the different steps of the BC Energy Step Code. And in this case, they used Athena, but then they also explored using actual data points from insulation EPDs, manufacturer-specific EPDs. They also looked at the CLF MEP calculator as well to try to estimate the embodied carbon associated with MEP. So we kind of looked at some of these numbers as well. We looked at the city of Vancouver rezoning data. So as I mentioned earlier, we had anonymized data. So I graphed out the anonymized data. And you could see, for example, for the apartment buildings, the average was around 350 kilograms of CO2 per meter squared, and the office was around 450, although there wasn't as much data points on that front. So we looked at some of this data. And just one point to mention as well, as we're talking about these benchmarks, which look at kilogram of CO2 per meter squared, that meter squared floor area, it's really important to distinguish what floor area is included in that. Does it include parkade area or not? Because that can obviously sway the results quite considerably. If you don't include parkade area, then there's a bigger spread in results versus if you do, based on the study done by Zara back in 2019. So there was also, we looked at benchmarks from One-Click LCA. So this is one of the software tools that are commonly used, mainly for Part 3 buildings. And so they've created these letter grade rating systems. And this is based on LCAs that have been done using their software tool, using their database. I would say that most of these benchmarks are heavily skewed to European projects. So there's less data points in North America. However, I think it is still useful to look at these numbers. And they have different benchmarks for each different building archetype. So for example, for offices and apartments, we looked at this, and they created these letter grade rating systems to show like what is considered a good building, what's kind of middle of the road, like D, and what is kind of considered high for these different archetypes. I basically took their benchmarks and kind of looked across all the building archetypes, and then I kind of cataloged it. It's just a different way of kind of representing the same data that they had shown here. But here I have like like the low range, the middle range, and the high. As you recall here, there's like a low and a high, and then I created a midpoint as well for these different stages. So for example, one of the things I did was for some of the archetypes where we didn't have a lot of great data, I actually tried to look at what is a relevant tier that seems to be kind of locally relevant for us. So for example, with the city of Vancouver data, we had a lot of data for apartments and low-rise residential buildings. So then I tried to look at, for those given archetypes, what is the corresponding threshold that seems to be around the median that we're seeing? And then I use that same threshold, that same tier for some of these other archetypes like primary school or retail, et cetera. This is another way of graphing it out, the same data that I was showing you, the A, B, C, D, E, F, G for each of the building archetypes. You can see the number of sample data points in each one of these. And so we kind of picked the threshold range so you can kind of see how they all stack up. We also looked at the CLF benchmark data set. This was a fairly old study done in 2017, but I think it's still useful to see the general range and order of magnitude and the medians that they're seeing across these different building archetypes. I did also see this data, this EU benchmarking study that was recently released, which covered mostly data from 5 countries. So you can see there's a big range in the results there, although I didn't end up actually using this study in the assumptions that we used because we had better estimates from other benchmarks. So that was those were the data points that we used, the sources that I looked at for the structure and envelope scope. But what about for mechanical, electrical, plumbing, and also for tenant improvements? Again, not a lot of great data on this front, but there was a study done by CLF, the Carbon Leadership Forum, looking at low, medium, high estimates. And this was just based on a few different buildings. So, but I use this as a starting point for some of the assumptions. And mind you, these are kind of for each time of replacement. So if you have multiple replacements, let's say every 15 years on your MEP systems and for your tenant improvements, these things can add up very quickly. And so I also made estimates for how often they would be replaced for those MEP and the interior section. On the mechanical side, for MEP, there's also been some better data that I've seen recently from that's published in the UK with Integral Group and the CIBC TM65.1 methodology, if you're familiar. That's a methodology for kind of estimating mechanical, electrical, plumbing related embodied emissions. And so they did a study for residential archetypes. And so they kind of showed a range of emissions that kind of a minimum, average, and max for different building archetypes based on many different mechanical systems and electrical systems that they modeled. And they did that without refrigerants and also with refrigerants. Now, something to keep in mind is that you can see some of these refrigerant numbers can be very, very high. I'll get into this in a bit, but their refrigerant leakage assumptions are a bit higher than some of the assumptions that we've seen modeled here, at least in Vancouver. So moving on that front, on the refrigerant leakage side, there's a study that's been done by Integral Group for the city of Vancouver, looking at different systems, different mechanical systems and the leakage rates associated with it. In this case, this was for a high-rise multi-unit residential building. You can see there's a range from 0.4 to 2.6 kilograms of CO2 per meter squared per year of leakage rate assumption. And so in this case, we ended up using this data rather than the UK CIBC data. And so we essentially just assumed 1 kilogram of CO2 per meter squared per year for apartment and non-residential archetypes. In contrast, if you compared that with the CIBC leakage rate assumptions, which are much higher, they went from 0.3 to 6.5 kilograms of CO2 per meter squared per year. So can be quite high. I know there's a lot of details here. I'm not going to dig into these assumptions, but they're all here for your reference later on. And again, I want to emphasize that this is kind of just my best guess at this. I would love to see other people take a look at this, or if there's other better ways of estimating this. But this is kind of the best that I could see, at least with the data that we have right now. Okay, let's get into projections now. Okay, so we're looking at various different timeframes from 2020 to 2050. Now, the data that we received from Navius is actually building stock. So we looked at how much building floor area there is for each different archetype. So we have modeled here single family detached, single family attached, apartments, offices, et cetera. So all the different building archetypes, each column represents a different archetype. And then each one of these bars represents the time frame. So from 2015 to 2020, all the way to 2050. Now, what I want to show here is that there's different colors here. These different colors represent the vintage of these buildings. So, obviously within the single family homes, some of these are older. They're built in, pre-1980s. Some are between then and 1990. Some are post-2000. And then the green ones are looking at the new buildings that are being built since 2015. And so they have classifications for it being new or near new efficient or near zero to represent kind of the different types of efficiency levels for the new construction. And so the key thing to note is that if you compare it relative to 2015 and you're looking at the building stock numbers, right? So this looks at all the existing buildings that exist in each of these 5-year increments. So if you look at the change of the building stock, that's how you're going to figure out how much demolition there is and how much new construction there is. So the decrease in the red bars shows you how much demolition there is. And the increase in the green bars, from here is the amount of new construction. So this is shown in a 5-year interval. So then basically what I did was then turn that into annual new construction and demolition rates by different vintages. So you can see for single family homes, how much new construction is projected in each decade. and what vintage, and then how much demolition is taking place for single family homes, single family detached, attached, etc. So you can see that. Using that data, this is just another way of presenting the same information. The top line is the building stock, so the total building stock associated with each archetype. And then the bottom graph shows you the annual new construction in meters squared and the annual demolition in meters squared. And if you kind of compare the annual new construction and annual demolition relative to the building stock, you can see, at least in our current decade, the amount of new construction happening annually is equivalent to 2.55% of the building stock in BC, and the annual demolition is around 0.64% of the existing buildings that we're demolishing each year. To show that in a different way, this is kind of the same graphs, but now stacked together. So new construction, demolition between 2015 and 2020, 2020 to 2025, et cetera. And these are annualized numbers. So you can see, for example, in our current decade, we're projected to build about 11.5 million meters squared. 11.5 million meters squared, and demolish 2.9 million meters squared of floor area. So then I took that data and then I mapped it with those assumptions that I showed you earlier. So I created, the estimates for the base scope and the full scope for each of those estimates. So that was that big Excel table I showed earlier with all the assumptions. So this here, you can see what was the assumption, like the kilogram of CO2 per meter squared that was used for each of these archetypes. And then we basically multiplied that with the floor area, the annual new construction and demolition. And you can see that. So this is kind of the zero line. It mainly makes sense to look at the new construction line, but the demolition was kind of interesting just to see it. You could think of it as an estimate on the embodied carbon sunk costs associated with that demolition. But you look at the new construction, and you can see this was where I got that number. So the base scope in the year 2022 right now, we're estimating is around 3.93 megatons of CO2 per year. And the full scope is 7.19 megatons of CO2 per year. Now, the question is, what happens if we actually implement some policies to reduce embodied carbon? Well, first off, the total embodied carbon associated with the whole province will change depending on the amount of new construction taking place each year. So irrespective of the emission intensities, there's a certain amount of change up or down that can take place just due to how much new construction we're projected to do, right? But I wanted to look at, okay, how do we isolate the impact of policies? So if we kind of hold constant, we just look at if we were to, for example, reduce emissions, let's say we reduce 20% for across all these building archetypes. We had some policies that said, by 2030, you need to reduce by 20%. And then maybe by 2032, you need to reduce by 40%. This was kind of just a ramp up schedule that I had modeled. What would be the impact of that, right? So you can see if you have the base scope here, what I'm modeling here is like, what's the difference between the base scope, like the business as usual, and then the base scope using where we have that reduction due to policy. So for example, by 2030, you just have a 20% reduction. So that 20% reduction equates to 0.71 megatons of CO2 reduction as a result of that policy. And then in the next decade, if you then implement a 40% reduction by 2032, you can get 1.67 megaton of CO2 per year reduction as a result of doing this across the board. Now, this is just to kind of get high level estimates for what's the impact of these policies. So, okay, we have those top line numbers. How does this compare with other line items in the province, in the provincial GHG inventory? So what I've modeled here, this is just looking at the provincial GHG inventory. So you can see the scale of emissions province-wide, from 1990 to 2019. And so you have afforestation and deforestation, agriculture, buildings, electricity, fossil fuel, et cetera. So you can see that that's what the different colors represent. And you'll see the total megatons of CO2. So for example, in 2019, it's 68.6 megatons of CO2 province-wide. I also have percentage numbers in these bars, so you can see what percentage it is of the total for each year. I'm basically representing the same data here, but just looking at the 2019 slice. So in the year 2019, these are all those different sectors. So what if I shortlist and look, I then want to compare embodied carbon. So the total embodied carbon compared with some of the relevant sectors in that other side. So as a refresher, these were the two numbers I was looking at, the base scope and the full scope. So the base scope, 3.9 megatons, full scope, 7.2 megatons. how does that compare with other industry sectors? So for example, for buildings, this is just looking at operational carbon emissions. It's split by residential and services. So you can see it's in total, it's about 8 megatons of CO2. But then I also wanted to compare against like cement, which is around 2 megatons, or iron and steel. It's almost 0 because we mostly import steel. We don't produce steel here. Pulp and paper, etc. So you can kind of read through here, solid waste, 4 megatons. Now, I think the one that makes the most sense to compare against is operational carbon emissions. So here I actually dive deeper. So looking at the operational carbon numbers, I mentioned that the total operational carbon emissions is, it was 8.31 megatons of CO2, and the base scope is 3.9. But what if we actually kind of split this by commercial and residential buildings, and we brought this down to a whole building basis? Because I actually have the building stock numbers, so I know how much floor area there is in commercial buildings and how much floor area there is in residential buildings. So I essentially took those building floor areas, divided it by the total emissions each year. So then you can kind of see the average GHGI annually. This is for existing buildings. So 33 kilogram of CO2 per meter squared for commercial, and 13 kilogram of CO2 per meter squared for residential. Now, mind you, this is averaged across all the different building types for existing buildings, and the newer buildings, especially if you're in the city of Vancouver, it may be much lower as you electrify the buildings. But then you look at embodied carbon on the base scope and the full scope. You can see what the estimates were based on the estimates that I had earlier. And then if I divided those two numbers, so embodied carbon divided by operational carbon, you could see the number of years that the embodied carbon is equivalent to relative to the existing building. So 14 years for commercial, 22 years for residential. Now, I want to caveat that this is not, this is divided, comparing it to existing buildings, but the new buildings are likely to perform much better because we have operational carbon GHGI. So it's not like you would necessarily design the new buildings to be performing at 33 either. So the numbers will sway a little bit, but I think it's still useful to kind of get a sense of what these numbers look like province-wide. Now, this was only looking at the base scope. We also have the full scope. So if you look at the full scope, including MEP and interiors and refrigerant leakage, then it brings it up to, let's say, between 28 to 38 years. And these numbers you saw earlier, that's just kind of the top line numbers. One more thing I wanted to mention is that in looking at the assumptions that Navius gave to me, they also had their projections for the emissions for different sectors like cement, aluminum, et cetera, by different years. And so one thing that I noticed was that there was not a big change in the cement and the aluminum emission intensities, at least the kilogram of CO2 per dollar after 2020. So this may be something to keep in mind, is that, you know, if we can actually develop policies, and maybe there's room to do kind of material specific buy clean type policies, perhaps there's potential to further reduce these manufacturer related emissions beyond what's kind of baked into the Clean BC plan right now. So to summarize this, you know, the base scope for embodied carbon, so structure and envelope, 3.9 megatons of CO2, full scope, 7.2 megatons. If you compare that to operational carbon, which is 8.31 megatons, you can get a sense of the scale there. If we implemented policies to reduce embodied carbon in new buildings, let's say it's 20% by 2030, you could get a 0.71 megaton reduction. And if you got to 40% reduction by 2030, or sorry, 2032, that should say, then it's minus 1.67 megatons of CO2. And one thing I also wanted to mention is that we also had that demolition floor area in here. And so demolition is projected to keep increasing, you know, from 2.6 million meters squared to 3.2 million meters squared by 2030 to 5.1 million meters squared by 2040. And so there's right potential for retrofitting these buildings instead of demolishing it. And also we need to look at the demolition waste. So given if there's that much demolition happening, what are we doing with the construction and demolition waste? How can we reuse more of it? How can we recycle it more of it? We need to think about circular end of life approaches to tackle those emissions as well. Okay. Next up, whole building LCA case studies with reduction scenarios. So initially I mentioned we were thinking about actually taking some of these archetypes. So for example, in the BC Energy Step Code metrics report, they had modeled from an operational carbon, like energy modeling perspective, these different building archetypes that are used. I was thinking about initially taking this and then developing a model on the LCA side. But one thing you'll notice is that with energy models, they're oftentimes very simplistic and they serve the purpose for operational carbon or energy modeling, but it doesn't have enough detail that we would need for embodied carbon studies, right? Because we need accurate material quantities. We need to know like what the specifics around the structures, how thick are those slabs, where's the transfer slabs, how much materials from the columns or from the interior shear walls, et cetera. So there's a lot of details that we need in that. And so while we initially were thinking about that, what we ended up doing was actually taking some of the whole building LCAs that we've worked on within my company. And so we took that and we anonymized some of the studies. And then we did some additional modeling on some of these studies. So these studies that we did are hopefully representative of some of the different building archetypes. One building that we didn't anonymize was this project, because this is a City of Vancouver owned project. So this is the Cole Harbor building in that, which is like an educational building or daycare, and it's a mixed use building. So you can see, within a Revit model, we have a lot more detail in here, right? So we're actually taking this, we're looking at how much, below grade wall area, above grade wall area, window area, concrete volumes, et cetera. So there's a lot of detail in this, and you can see it's much more detailed than something that you would get it from a simplified archetype model. And so that's, we wanted to use this as more realistic modeling. So all the case studies that I'm going to be showing represent projects that are at least in the design development stage. Some are in the construction stage. But I also want to emphasize that the numbers I'm showing are not specific, may not be indicative of what these projects are actually going to achieve. They're just different scenarios. So for the purpose of this study, we actually modeled some different additional design scenarios to kind of look at what's the best achievable concrete mix that we could put in this, or the best achievable rebar or whatnot. Just to kind of indicate what's the reduction potential just from some simple material substitutions. So as I mentioned, all the projects here are anonymized with the exception of that one that I showed and are currently in progress. And this is more just to kind of give us a sense of what reductions are achievable on real buildings. And we also tried to look, and the other thing is that we only looked at a few simple material substitution options. There's actually potentially more reductions that these projects can achieve because we haven't evaluated any things related to material efficiency, space efficiency measures, material reuse, et cetera. But the baseline buildings are functionally equivalent because they're basically comparing against itself, but we're just having material substitutions that are reflective of industry average data points. So before I dive into that, I want to look at some of the key categories that we looked at. So we looked at some assumptions around concrete, rebar, insulation, and wood as it pertains to biogenic carbon storage. So for concrete, we have the CRMCA industry average data. So this is the Canadian Ready Mix Concrete Association. They have industry average data for different concrete mixes. And so they have their industry average benchmark. So that's what we refer to as the baseline. And then we compare it relative to, if you don't have manufacturer specific EPDs, you can see the impact of using Portland limestone cement versus Portland cement, or higher supplementary cementatious materials like fly ash or slag. So you can further reduce emissions that way. Now, we also have some data from some local ready mix producers in the Lower Mainland, so such as Lehigh Hansen, like Ocean or Lafarge. So we modeled some, I think in this scenario, we mainly kind of looked at Lafarge to just show kind of what were some of the highest reduction potentials we could see in some of these scenarios. Now on rebar, you can see this is the industry average data point that we use for rebar, which is around 0.979 kilogram of CO2 per kilogram of rebar. But we also compared it with a supplier in Alberta, which is around a 20% reduction relative to the baseline. And then we also looked at the lowest data point that we found in One Click LCA's database, which is Nucor Seattle Steel, which is around a 50% reduction on the rebar. And then the final thing is on insulation. So this is looking at a few different types of insulation options: XPS, spray foam, polyiso, EPS, mineral wool, et cetera. This is looking at kilogram of CO2 per meter squared at an RSI equal to 1. Now, the key point is there's been some changes happening on the insulation market. So for XPS insulation, prior to 2021, almost all the XPS insulation and spray foam in North America, most of it used HFC blowing agents, so hydrofluorocarbons, which is essentially like refrigerants. So they're very high impact greenhouse gases. And so those impacts are very, very high. But since the Canadian government has introduced some new regulation around this, there's been a new batch of products developed by the leading manufacturers. And so this shows you where their numbers are at now in this new batch. So they all have kind of new XPS alternatives. Similarly for spray foam, there's manufacturers are now producing HFO blowing agents instead of HFC. So these have about an 80 to 90% reduction relative to the older forms of insulation. So, so in some of the case studies that I'm going to go over, we looked at sometimes we just modeled the worst case XPS option just to show how significant that those emissions could have been, even though that's not what we use as our baseline because that's no longer allowed due to regulation. So what we used for baseline is actually the highest impact of the current batch of XPS products. So we modeled that, and then we also modeled what the impact of using some other different types of XPS products as well. And the reason why I'm talking about XPS and spray foam quite a bit is because those impacts are quite significant, and at least the older variety can be much, much higher than the other types of insulation. So we looked at that. And then finally on wood, we looked at biogenic carbon. Now, this is a fairly nuanced topic. There's a lot of active research and debate on best practices right now on this, but I just wanted to kind of illustrate the impact of different biogenic carbon accounting approaches. And I want to emphasize these are not standardized approaches right now, but this is kind of what some researchers are working on in kind of the academic field right now. And so just wanted to look at what would happen if we actually account for some of these biogenic carbon emissions. You know, when we're looking at wood products, typically we don't look too deeply into what's happening in the forest. And so in this case, I looked a little bit at this thing called GWP Bio, and I applied this type of methodology to some of the modeling scenarios that we ran, just to show what the impact of these assumptions would be. And this GWP Bio approach what it's trying to look at is essentially create a multiplier that you multiply against the wood or the stored carbon content associated with all of the wood products in the building. So you may have heard, you know, some projects, sometimes they want to claim credit for the carbon stored in the wood because it's sequestering that carbon and putting into a building in a long-lived harvested wood product. But there's also an impact on the rotation period. So like when you cut down a tree, that takes time for that tree to regenerate. And so so the rotation period has an impact on the carbon modeling, biogenic carbon modeling, and also how long you store it. For example, if you incinerate the wood product, like in bioenergy, there's a lower benefit compared to if you stored it in a building, in a long-lived building for 60 years or 100 years or whatnot, right? So it's trying to come up with a multiplier that accounts for this. And this is more of a dynamic modeling that takes into dynamic as in like it includes a temporal aspect, a time aspect to our modeling, whereas most of our LCA studies are very much a static approach, which don't take that into account. So I'm not going to get into too much of the details. I just for all intents and purposes, you know how sometimes some people will take that stored carbon number and turn it into a CO2 equivalent, you know, that the amount of stored carbon in the wood in a building. Sometimes they take that number and they multiply it by a -1. And so for the purposes of this study, I'm just calling it optimistic. So you'll see some modeling, if we accounted for biogenic carbon and it multiplied it by a -1, that's the optimistic scenario. And for this case, I also have created a GWP bio scenario where I'm multiplying it by a -0.65. The details of this is kind of beyond the scope of this presentation. I did a deeper dive on this for the city of Vancouver, and the presentation's on the CLF Vancouver YouTube channel. So it's like an hour-and-a-half presentation summarizing the current state of the art, or at least the best research that I found around biogenic carbon and how the different tools handle it. So if you're interested, you can look there. But as I mentioned, the GWP bio multiplier that I used for this study was -0.65. So first off, let's look at this project. 11-story mixed-use building, and this is a concrete frame building. So the different options that I looked at was what's the impact of if you change concrete mixes, what happens if you change the rebar, and what happens if you change the XPS, because this is actually a passive house building. So there's a lot of XPS. It's a highly insulated building, which is great, but there's also an impact on the different types of insulation. Or the insulation options can impact the results quite a bit. So here you can see the baseline number. So for example, for this building, it's 475 kilograms of CO2 per meter squared. That's the baseline number. But then we modeled some individual options independently. So for example, if we keep everything else the same, but we just model the impact of different types of XPS options, you could get up to a 10.3% reduction on XPS. What about rebar? You could get up to a 7% reduction on rebar at the highest case. And on concrete, you can get up to a 20.8% reduction on a whole building basis. So if you stack those three material substitution options together, you can get a 38.2% reduction on this front. Now you'll notice there's also this one number that's really high on this end. This is not the baseline building, but if we, for example, use that XPS, actually the next graph probably shows it better. This is showing the same graph, but basically showing you a breakdown. So instead of just showing you the total embodied carbon, I'm showing you the breakdown by material category. So you can see the kilogram of CO2 per meter squared for each of these scenarios, and how much is associated with each of these material types. So for example, the dark gray is the ready mix concrete, the blue is the steel, the purple is the insulation. So you can see the makeup. So for example, in the baseline building, concrete, steel, and insulation together combine for about 82% of the emissions for this baseline building. But you can see in this scenario, all of a sudden there's this huge purple bar. Well, that big purple bar is what would happen if we actually use the XPS that was commonly used prior to 2021. So that's the XPS that has that really high HFC blowing agent. Well, that 475 would then turn into 739 kilograms of CO2 per meter squared. So something to keep in mind is that, even in our baseline modeling, we're not modeling the worst possible baseline. We're modeling kind of the worst possible based on the kind of the current standards in a way, or what's allowed in regulation, at least here in Canada right now. Mind you, in the States, there's different states have different policies or different regulations, but many states still don't have regulation on HFC blowing agents, at least to my understanding. Maybe some things have changed since then. But so it does matter, like the sourcing of the different types of insulation, because some of this product is still available in the market. But as you can see, as you kind of further reduce, what I'm showing here is where are those reductions coming from? So how much reductions are happening due to concrete? So in this case, for example, due to the concrete mixes, we are reducing by 99 kilograms of CO2 per meter squared, which is equivalent to 21% of the total. If we change the rebar, the best available rebar, it's another 33 kilograms of CO2 per meter squared. And then for XPS, another 46 kilograms of CO2 per meter squared. So we can get close to that 40% reduction threshold just by using the products that are available on the market right now for this concrete frame building. We're not even going into mass timber territory or whatnot, but this is showing on a real project what can be done. And this graph shows, instead of breaking it down by material type, we were breaking it down by omni-class. So this is different building elements. So you can see how much goes towards the foundation, which is the black, the slab on grade, the gray, floor construction, that's the orange, roof is the red. So just different ways of slicing these numbers. By the way, I spent a lot of time in developing this visual to actually show the breakdown like this across all the scenarios. So you can see what's really happening across all these scenarios and where the breakdown in emissions are and where those reductions are coming from. Okay, so that's one example. That's a concrete frame building, 11-story. What about this one? So this is a 8-story care facility with 1-story parking, 21,000 meters squared. We went through similar design options. Basically for this project, we could get up to a 27.8% reduction if you stack those different measures. And this shows you, the same graphs that I showed you earlier. So, you can get 6.6% reduction just on this concrete. But then I think I went with a more aggressive concrete mix here, and then an even better concrete mix here. And you can see it. In this case, most of the reductions are coming from the concrete. And then you can achieve a 27.8% reduction or 192 kilograms of CO2 per meter squared reduction relative to the baseline. And this purple line is the same thing with the XPS. So if we use that worst case scenario XPS, that's how big the impact would have been. And then this is the breakdown by the building elements. So where are those emissions taking place and where are the reductions taking place? I'm going through this fairly quickly. You can look into the details of this later if you'd like. All right. Now, what about a mass timber building? So this is a 14-story multi-unit residential building with 1-story parkade. In this case, I compared it mass timber versus concrete, which use post-tension. So this is actually a US project. But then I also tried to convert it into a Canadian project in a way by using Canadian concrete mixes, just to kind of see what the impact would be, because there's differences in the different concrete mixes that are available. So as an example, the bottom two is kind of like from the original study. So if we don't account for biogenic carbon, we can get about a 20% reduction right now from the mass timber building relative to the concrete frame building. If we adapted it to the Canadian version and we use Canadian concrete mixes, kind of the best available that we're seeing in the Lower Mainland, that could bring it down to 32% reduction on a whole building basis. But the interesting point is, okay, well, what happens? Oh, actually, sorry, this is showing you the same thing. So in this case, you can see where those reductions are taking place. So this is the 0 axis. So you can see what reductions happening from reduction in concrete, but then there's also an associated increase with like the steel frame and with the mass timber. So it nets out to 32% reduction, for example. And this was the same thing, but split by Omni class. But here the interesting point is what about biogenic carbon? So what about different scenarios for how we account for biogenic carbon storage? So the blue bars just represent if we just look at fossil fuel related emissions and we don't account for biogenic carbon storage. But if we did account for biogenic carbon storage, this is how much would come out. So on the wood scenario, the baseline is concrete, so there's no wood, so there's no negative number. But for example, if we're using this GWP bio multiplier, so you take the total carbon or total kind of stored CO2, biogenic CO2 in the wood, multiply that by negative 0.65, this is the number that you get. And so then if you net that out, you go from a 32% reduction to a 46% reduction, because this basically is taking 301 minus 62. And so this would be a lower number. And so you would obviously have a bigger percentage reduction if you accounted for it this way. And then a similar level for this other project, for the US version of this project. Now I've changed it to the optimistic scenario. So what happens if you use the -1 multiplier instead of the -0.65? Well, then the negative gets to -95 kilograms of CO2 per meter squared. And so then the percentage reduction jumps from 32.3% to 53.8% reduction. So the reason why I'm showing this is that it really matters what our assumptions were, what assumptions are being used in terms of our biogenic carbon modeling, because it'll obviously affect your total absolute kilogram of CO2 per meter squared. It'll also affect the percentage reductions relative to a baseline. This is another project looking at 2-story community center, 4,000 meters squared project. This is light frame wood with some minor mass timber elements, but it's mostly light frame wood. And we're comparing it against a concrete structure with the steel stud walls. You can see the total top line numbers. We can get up to a 40 or 39.3% reduction based on the accumulation of those different measures. To show you the breakdown of where those measures come from, a lot of it comes from reducing emissions from concrete because we're switching from concrete frame to a light frame wood, and then same thing on the steel side, reducing the steel associated with it as well. But we're increasing emissions a little bit on the wood, and so that you can see the net number is this dotted line, which corresponds to this. This is the kilogram of CO2 per meter squared and the percentage reduction. Same thing by Omni class. Okay, so this is interesting. So this is a light frame wood structure. And so even in the baseline, even when we're using concrete frame, there's still some wood elements in this building. And so there's this is the biogenic carbon associated with it. But then in the proposed scenario, we have much more wood in there. And so what's the percentage reduction? Or sorry, what's the biogenic carbon storage associated with the -0.65 multiplier for GWP bio? So you can see, as I mentioned earlier, at the max case scenario, we can get to 39.3% reduction. But if you account for biogenic carbon using this -0.65 multiplier, that brings it to negative 83.5% reduction. So huge difference, almost double the amount of reductions. And then what if you use the optimistic scenario? So the multiplying it by the -1. Well, if you did that, then the stored biogenic carbon is actually greater than the total fossil fuel related emissions for this project, which at 197. And so this would get you into negative 114%. So that just gives you a sense of what the scale of emissions can look like. Oh, this is another mass timber building, 3-story office building, a small one. But again, kind of just playing out that same scenario. So what happens if you compare it against a concrete building? Well, you can get, actually the main scenario is to look at this one, there's 31.1% reduction. So you can get 31.1% reduction going from mass timber to this concrete frame version of the office. And this is but what if you include the biogenic carbon? So if you include the biogenic carbon stored in that wood, then it goes from 31% reduction to a 65% reduction. So almost double the percentage reduction based on using the GWP bio, the negative 0.65 method. If you use the -1 method, the optimistic method, that grows to 86.6% reduction. Okay. So I know that was a lot of numbers, really hard to kind of keep it all in your head. So I actually kind of summarized those 5 case studies, kind of the best case scenario versus the baseline. So there's basically 2 line items for each of these buildings. So for each of these buildings, there's the baseline and then the best proposed scenario, and then what the percentage reduction is associated with it. So you can see across these projects, you can get, between a 27.8 to a 39.3% reduction. So close to 30, close to 40% reduction, achievable just by some simple material substitutions or going from mass timber versus concrete, for example. This is the same graphs, but broken down by material type, and then the same graphs broken down by omni-class, and then the same graphs, but now showing what the impact of using GWP bio is for these different scenarios, and then using the optimistic -1 scenario. And the main point here is that, if we use biogenic carbon, that can significantly reduce or increase the percentage reductions there. Okay, beyond that, I also just wanted to quickly touch base on 2 other case studies. And in this case, I'm not comparing different design options between these different case studies, but both of these are actually low-rise multi-unit residential buildings. So they're both low-rise light frame wood buildings, except one has a 1-story parkade, a common parkade across multiple kind of buildings on top of this common parkade. And then this one is just a regular light frame wood building, but no parkade. And you can see, the light frame wood, there can be almost a 3x difference between the numbers. So for the one with no parkade, it's 129 kilograms of CO2 per meter squared. And then for the one with 1-story parkade, it's 391 kilograms of CO2 per meter squared. And that's partly due to like this big parkade and the transfer slab. There's a big thick transfer slab underneath it, or at the roof of the parkade. So all of these things can add up quite a bit. So, there can be big variations even within what seems like the same kind of building archetype. So to summarize the whole building LCA case studies, you can get between 28 to 38% reduction in embodied carbon based on just currently available materials in BC without accounting for biogenic carbon. And if you do account for biogenic carbon, it can significantly increase those percentage reductions up to 83 or even 114% reduction. Okay, next up, cost impacts from reducing embodied carbon. Well, this was a great study done by the Rocky Mountain Institute where they cited 3 case studies. And for these 3 case studies, they showed that they were able to achieve between a 24 to 46% reduction in embodied carbon at a cost premium of less than 1% on the total project cost. So that indicates that there can be a lot of low-hanging fruit on these projects. And these are some of the top categories that they looked at. So for example, for concrete, you can get 14 to 33% reduction at none or low cost premium. High recycled content rebar, you can get between 4 to 10% reduction at none to low cost premium. You can select low or no embodied carbon insulation options. You can, in this case, for those case studies, they were able to achieve 16% no cost premium. Glazing, you can reduce a bit, and then finished materials as well. And so these were those 3 case study buildings that they showed. So they actually showed you where those reductions took place. So in aggregate for this case study, this mid-rise concrete and steel construction, they were able to get a 46% reduction at less than 0.5% premium on the total project budget. In this mid-rise stick-built construction, it's 41% reduction at less than 0.5% total project budget. Tilt-up concrete, 24% reduction at less than 1% budget. All right. I'm actually going to skip through this. I think a lot of but basically within each of these categories of materials, there's a lot that can be done to reduce costs. Now, I also came across a study from BTY, which is a cost consultant. And so they worked on this mass timber costing study. And so given that mass timber is one of the potential options for reducing embodied carbon, this is a strategy that many teams are looking at. And so in this case, they actually looked at the cost comparison for a mass timber structure versus a reinforced concrete structure. And then they also had a hybrid structure with like a mass timber with concrete floor cores. And then they also had mass timber with steel frame. And there's an impact on the construction schedule. However, well, actually, what was the main thing I want to see? Oh, so what were some of the main findings that came from this study? Well, the mass timber and concrete core version had a 12% cost premium relative to the base building. The prefab hybrid concept building had 20 to 25% cost premium. And one of the things that they said is that, mind you, this is not necessarily the most optimal way of building with mass timber. So for example, using a concrete core design did not actually allow them to achieve as much potential schedule savings for the mass timber side of things. And so that impacted the scheduling, and using a concrete formwork structural cycle can lower the productivity and therefore the cost competitiveness of the mass timber. So this study is not saying that all mass timber projects are more expensive or that much more expensive. I think there's a lot of parameters that can be at play, but that's just something to keep in mind and to actually address and make sure that these projects are designed from the start to be mass timber, because if you do that, there can be a lot that can be done to reduce the cost premium or to make these projects competitive. There's also, this was a separate study. And mind you, I'm just citing studies that I found on this. There could be a lot more costing studies available, but we didn't do any actual costing work on this project. I'm just citing what information I've seen out there. Now, insulation and embodied carbon. So this was from that Builders for Climate Action study with Natural Resources Canada. These numbers, mind you, these numbers do include biogenic carbon storage in these insulation options, which is one of the things that happens with that's utilized in that beam tool. But they're showing the embodied carbon numbers, including that biogenic carbon number, and then the cost per 10 meters squared of R10 insulation. And the key point, that take-home point from these tables, is that there's no direct correlation between the cost and the embodied carbon of insulation, and that it is possible to actually select materials that would balance both cost concerns and favorable embodied carbon results. So, it's not always the case that the highest embodied carbon is the highest cost or the lowest cost. Sometimes it's the middle of the way. So you can see, based on this table, there's wide variations in both costs and in insulation. And so what we need to do is actually look at those values and then actually try to optimize for this. Same thing is true for cladding. So they also did the same thing for cladding. So you can see there's a big range in the emissions associated with cladding and a big range in the cost as well. Again, you can optimize for both. And so the take-home message with the cost impact is that there's a lot of low-hanging fruits to reduce embodied carbon. Some studies are showing that there's little to no cost premium, or maybe it's like 0.5 or 1% total project cost premium. But on the individual material level, there can definitely be cost premiums. On some of the concrete projects that we're working on some of this projects that we're involved with, like we're seeing maybe sometimes 0.5%, sometimes 10% on premium on the concrete cost. So this is just the cost of the concrete, not on a project-wide scale, but that can still significantly reduce emissions on a concrete project, right? So, at the lowest tiers, there is definitely a lot of low-hanging fruit that can be low or no cost. But past that certain threshold, there sometimes is a cost premium, but it's something that we need to weigh on a project by project basis. But across all the material categories, generally you can actually optimize for both. So it's important to look at both. Okay, next up is proposed percentage reduction thresholds for this provincial policy framework. The city of Vancouver, as I mentioned, is as part of their climate emergency action plan. They're targeting a 40% reduction by 2030 on embodied carbon. And so at the time when I was actually doing this presentation, the city of Vancouver the staff had not gone to council with this, but I think this is approved now. So effective July 1st, 2023, the city of Vancouver has kind of incorporated embodied carbon into the Vancouver building bylaw. And so for all projects going through to building permit, they're going to need to report embodied carbon and also not be more than 100% higher than the baseline. So basically, this is just a way of having the projects actually get familiar with developing a baseline while still not having any real limit that they need to, or a hard limit for them to fall under. But then starting in 2025, at the beginning of 2025, there will be between a 10 and 20% reduction requirement, depending on the building archetype. And so this is trailblazing policy, right? Like this is, it's amazing that the city of Vancouver has incorporated this into the code and is going to be requiring all projects to be complying with this, right? And so, and they also have some responsible sourcing criteria as well associated with sustainable and ethical materials, circular materials, and healthy and transparent materials. Now, the question is, or not question, but I think we can actually build on the framework that the city of Vancouver is approaching with their policy at the provincial scale. Now, I want to emphasize again, this is not, we're not saying that this is going to go into the BC Energy Step Code or anything like that. But if we were to use, I think it is useful to actually think about what has made the BC Energy Step Code successful and how we could use some similar framework to address embodied carbon. So, you know, one of the good things about the BC Energy Step Code, which was very pioneering at the time, was that instead of kind of doing this incremental approach with code updates that kind of, you know, satisfy the lowest common denominator and make sure that, you know, everybody can achieve it, and they tend to be very incremental in nature. With the BC Energy Step Code, they kind of applied more of a backcasting approach where you have a target and then you work backwards from there for each of the steps to see how do we actually achieve this. And then we actually enable different municipalities to kind of opt in at different stages or different steps, depending on where their readiness level is. So this graphic, I just basically kind of took a similar branding to the BC Energy Step Code and just kind of applied it here, but these are not official graphics for the BC Energy Step Code again. But this was potential thresholds that we thought would be that we proposed to the province. So basically, if you imagine with this for part 3 buildings, step 1 could be disclosure, step 2 could be 10%, step 3 could be 20%, step 4 could be 40%. So this would align well with what the city of Vancouver's tackling with their 40% target. Now, at the time, I actually thought maybe, I wasn't sure if this was a good approach or not, but I introduced a 2-year time lag in here. So we were saying like, well, this could be kind of rough estimates for when we could achieve these different thresholds. However, I think there's also a strong argument to be made to actually, if we were to do something like this, to potentially keep a more ambitious timeline to get 40% reduction by 2030, because it would send a coordinated, targeted signal to the industry that this is, and create a lot more demand across the industry. So it's not just the city of Vancouver pushing for this, this is province-wide. Now for part 9 homes, kind of similar approach, you could get to a 40% reduction through these different timeframes or these different steps. Maybe don't pay too much attention to the timeframe, but it's more about the percentage thresholds that could potentially make sense here. Now, with that, you know, whenever you have percentage reductions, the question is, how do you define the baseline? So the city of Vancouver is working on developing their own set of embodied carbon modeling guidelines, and I'm working on this as well with them. And one of the things is, and we're going to be seeking a lot of external input on this, just to be clear on this, to make sure that we come up with a good, robust approach for this. But one of the things that it'll provide guidance on is how to define baselines. And so based on some of the preliminary modeling that the city of Vancouver had done with another consultant, is that they looked at, you know, even with the baseline that they're providing right now, the baseline is defined in such a way that it could already eliminate a lot of the or 40% of the highest outcomes out of the scenarios that they modeled there, right? So how you define the baseline matters a lot. Now, there's oftentimes a question as to, should we use absolute targets, like a kilogram of CO2 per meter squared, or should we use kind of a relative percentage reduction approach where we have different baselines for each building, and there's all the challenges associated with defining kind of a reference building approach. At the time, this was not finalized, but I think this is now finalized. The the CAGPC Zero Carbon Building Standard has a version 3 that they've rolled out. And within that version, what they did was they actually looked at different thresholds. So they kind of did an either or approach, like 500 kilograms of CO2 per meter squared being below that, or a 10% reduction relative to a baseline. And then their 20% threshold, they also introduced a 350 as an absolute, so you can comply with either or approach. Now, one thing I just want to use, I'm just overlaying this on top of the City of Vancouver rezoning data just to kind of give an indication. One of the challenges with using an absolute target, while it's easier to implement, it's very hard to get that number exactly right. So for example, if we set it at 500, and I think the ILFI also has this with their zero carbon certification, they have a maximum of 500. Well, at 500, depending on the projects that you're getting, maybe very few projects are actually required to achieve any reductions at all. And most of the projects don't actually need to do too much to reduce it. If you set it kind of middle of the road, let's say 350 kilograms of CO2 per meter squared, some projects are required to achieve it and they're in the range where it's feasible, but then some other projects, due to certain project parameters, may actually find it very hard to get down to that level. And then there's still some other projects, if you just set one number across all the building archetypes, maybe, for example, all the low-rise residential wood frame buildings can easily escape past this target, right? So not to say that we can't address this, but these are just some of the challenges. And then if we set it even more ambitious, it can be really challenging for certain projects. So just conceptually, this diagram, I just want you to think about, if we're going to actually try to drive province-wide emissions on embodied carbon down, what we need is actually every project to achieve these reductions. Now, is it feasible for every project to achieve it? I think so, but I mean, we need to think through how we're going to define the baselines and how to ensure that this is. But conceptually, what you want is that each project, if they're developing their own reference building and their own baseline, it's actually a learning experience for each of these, for the whole design team, because they actually have something concrete or something kind of robust from which to compare against. And then they can actually learn what reductions are they actually achieving due to different design measures that they're doing. And that's what we need across all the projects. If we want 40% or 20% reduction, across province-wide, across all the buildings, that means every project needs to achieve that, so. Now, one thing I want to keep just to mention on the absolute front is that we have different blind spots within this field. So for example, one of the things previously, many of the tools had underestimated the emissions associated with XPS. And so they were sometimes much, much higher, like 10 or 25x higher than the data points that were actually in the databases, right? And so if you imagine setting absolute benchmarks using, and you use, some of the old data to set this, but then now there's new data that's released and, suddenly that data is actually much, much worse. That could potentially change your absolute targets, right? So that's just, I'm not saying this is an argument to never do absolute targets, but just recognize that there can be blind spots that we need to look at. Here's another option, like this is dynamic glazing that you may have seen. And so, this kind of dynamic tinted glazing can reduce operational carbon emissions, but they can also have extremely significant embodied carbon impacts. For this manufacturer specific EPDs, like 867 kilograms of CO2 per meter squared. So blind spots exist. Also, when we're looking at mechanical, electrical, plumbing systems, right now we have very poor data on this. And as we gather more data for this, we may find that, maybe there's some rare metals or components in these products, and that can also significantly drive up emissions. And so, all that to say is that there's many blind spots still, which can influence our absolute targets. I think I already summarized a lot of the key points here. One other thing is that, I talk a lot about kilogram of CO2 per meter squared, but we should also consider other metrics like dividing it by occupant or density. So this was something that was suggested in the City of Nelson study with Builders for Climate Action. also in that EU benchmark study, they also looked at not just kilogram of CO2 per meter squared, but they also indicated CO2 equivalent kilogram of CO2 per capita, or like per occupant in the building. So that could be something that we look at so that, you know, we can incentivize smaller spaces that are functionally useful versus like, you know, big mansions that have potentially a low per meter squared embodied carbon intensity, but still high on the absolute. Okay, I'm going to jump through this. Okay, consumption-based emissions and trade. So 2 more sections. I know there's quite a bit of material, but we'll leave some time for Q&A quickly. So production, something to keep in mind is that usually how different jurisdictions do their GHG inventory, how they quantify how much emissions there are, is typically what's happening within our borders, right? So the provincial GHG inventory is looking at all the emissions that happen within the borders of BC, but it does not account for things like imports. So for example, if you wanted to look at consumption-based emissions inventory instead of production-based emissions inventory, you would basically take the production-based inventory, subtract out the exports, and then add the emissions associated with your imports. So that basically looks at what is the impact of the things that are being consumed within our borders. And so there's been studies done at the city level. So the C40 cities, they actually have a study for 79 cities where they estimated the consumption-based inventory versus the production-based inventory. And you can see there's a, the consumption can be much bigger. So like if the production base is 2.2, the consumption base is 3.5, because maybe you're importing a lot of the emissions, right? Sweden is actually set to be the world's first country to target consumption-based emissions and incorporate this into their policies. The EU, on a slightly different tangent, they're looking at carbon border adjustments. So looking at some of the key construction materials, how do they address, if you're driving down the emissions of your local manufacturers, but then you're importing really highly polluting materials or much more higher emission intensity materials, do we have any sort of carbon border adjustments associated with this? So the EU is looking at this, and with their EU carbon border adjustment mechanism, they're initially focusing on 5 key materials or categories, 3 of which are particularly relevant for us: cement, iron and steel, and aluminum. So it's useful to actually take a look, at a Canadian level, what is the emission intensities of some of the key materials that we produce? So if we look at steel, we are among one of the lowest CO2 intensity producers of steel globally. So you can see this is where we're at. Now steel there's 2 main ways of producing steel. There's electric arc furnace steel and basic oxygen furnace steel. So if you look within each of these technologies, within EAF and BOF, we are again among the lowest in this. But what tends to really influence one of the factors that influence our total emissions associated with our steel sector is what the proportional split is between electric arc furnace versus basic oxygen furnace, because electric arc furnace is much lower emission intensity steel that uses mostly recycled steel and leverages the carbon intensity of the electricity grid. So given that we produce a lot of our steel in, for example, Ontario, with a fairly clean grid, we can have very low carbon intensity from our electric arc furnace steel. But we're at about, let's say, just under 40% of our steel is electric arc furnace, whereas in the States, it's about, I think it's 70% here. So that can change the total split. What about aluminum? Similar scenario, we're among the lowest carbon aluminum producers globally, almost the lowest, or just behind Norway maybe, but we're right around that range. So you can see there's a big difference between these different producers. And then you can see this showing up in our GHG inventory Canada-wide, and I kind of broke it down by different provinces to just show where are some of the key materials. So like this cement production, iron and steel production, you can see in Ontario, a lot is happening in Ontario. Smelting and refining, maybe a lot of that's probably due to aluminum in BC. So, now one thing that I wanted to, one more thing that I kind of tackled here was, I tried to develop a methodology for how to track these consumption-based emissions, because initially that's something that Jeremy wanted to know more about. Is like, okay, how could we actually get a handle around this, and where's the Venn diagram between our consumption-based emissions versus production-based emissions, even in like if we're just looking at construction materials and building materials. Well, typically at this macro level scale, when we're looking at emission flows, at the provincial or country level, and we're trying to look at the emissions associated with trade, we oftentimes use what's called environmentally extended input-outputs analysis. So these are using economic tables that look at the flow of money between industries and between countries, and we use that flow of money as a proxy for the emission, and then we have emission intensities for each of those sectors and each of those regions that are producing it. So we have a kilogram of CO2 per dollar within each of these sectors, and then we map that to the economic flows happening. So that's how that macro level study is typically done. Now, I think for the purposes of, if we're going to try to track for some key specific materials like concrete or steel or whatnot, it's probably a lot more accurate to actually use physical quantities. And so this was where I did a lot of searching on StatsCan website, and I found some amazing trade data, which are categorized by HS codes, which is how we track a lot of the international trade. So there's formal codes for like 50,000 line items of products. And what's cool is that they have both the economic value associated with it and also the physical quantities. So we know, within each province, how much aluminum are we producing or exporting, or how much steel are we importing, and from what country, and how many kilograms of rebar are we importing, how much economic value is that. And so I was thinking that this could be an interesting approach, is to take this physical quantity data and then map it to bottom-up emission estimates that are based on physical units, based on EPDs, based on LCA models, and that could actually give potentially a much more accurate estimate and modeling of these impacts. Because when you're doing kilogram of CO2 per dollar, that can be that can skew a lot of these numbers quite easily. So it's much better to use physical quantities. So as an example, I actually built this dashboard. This is actual data from 2020 in BC. So you can actually look at, if I filter out for iron and steel, you can see the kilograms of steel by different line items of steel, different steel products, and where we're importing them from. So each of these colors is different countries. So I can show, how many kilograms of whatever rebar we're importing and how much economic value is that. And these physical quantities are in kilograms, meters squared, meter cubed, units, etc. So, for example, this is all the steel that's imported from the US, all the steel that's imported from China into BC, all the steel that's imported from Vietnam. And then on the export side, we have the same type of data. So we can tell where are we exporting our wood. So how much of the wood is exported to the US, to China, to Japan. And so this will give us our physical quantities. Now, I think we can then map that to different bottom-up estimates. We could use industry average EPDs if they exist. However, one of the challenges, if you're thinking about importing steel from Vietnam probably doesn't have an industry average EPD. So I think what could be useful is that there's a Building Transparency, which is the organization behind the EC3 tool and database. They also have this open impact initiative where they're creating open access parameterized LCA models for a few key high impact materials. So starting with concrete or cement and concrete and steel. So what's interesting is that they're actually doing a full kind of LCA model, and you can actually look at some of the key parameters like the recycled content, the amount of electricity used at the mill, how much electricity is used from electric arc furnace, the electricity grid that you're coming from, and it can actually estimate those emissions. And so by kind of creating such a model, we could actually scale this for some of the key material categories and then map that information. So if we have indication for like how Vietnam produces its steel, those parameters, we could potentially create open access models like this, map those numbers with the physical quantities. So all that to say is that this is just a proposal that I have for an approach that could be used to kind of really get much better granular estimates based on physical quantities of these emissions. Okay, final part, forestry and biogenic carbon accounting. I'm going to go through this fairly quickly. Typically when you're looking at how we do whole building LCAs for wood products and EPDs, we're mostly focused on the emissions associated with the fossil fuel related emissions. So like emissions associated with cutting down the tree, transporting it, manufacturing, processing, et cetera, right? And landfilling. There's also biogenic carbon that's reported in the latest versions of these EPDs as well. Sometimes you'll see that this biogenic carbon, basically, if you think about all the wood that makes it into the building, that's in the building, they try to look at the amount of carbon stored in that wood and convert that into a CO2 equivalent. And then sometimes they multiply that by -1, which is that optimistic scenario that I modeled earlier. Or, if you're using some of these approaches like GWP Bio, it could create different multipliers that account for kind of the forest rotation period and also the product carbon storage period. So this is kind of what I showed you earlier. So, and that GWP Bio approach was using this calculator developed by WWF and Qantas. And so I dive deeper into this in my previous presentation for the city of Vancouver that looked at biogenic carbon. So that's online, so you can check that out afterwards. But as I mentioned earlier, we ran through some different scenarios, and ultimately I kind of had this -0.65 number, and I multiplied that in our whole building LCA studies, right? Now, we know that harvested wood products, the longer you store it in a long-lived building, or essentially the longer you store that biogenic carbon, there is a benefit from that. So, if you actually just burn it all in like wood pellets, for example, and so from a dynamic modeling perspective, that is worse off for the climate versus if you were able to store that wood in a building product. Now, maybe there are different streams of wood, so I'm not going to get into that, but I'm just saying, like, on a conceptual level, the longer you store the wood product, the better from a climate perspective. Now, there's a tool developed by ZGF and which is called the Upstream Forestry Carbon and LCA tool. And what it aims to do is actually try to account for these different, because biogenic carbon is fairly complex, and there's a lot of different methodologies and different tools kind of calculated in different ways. They created a little calculator, an Excel calculator with this, right? Now, what I wanted to introduce is that in addition to looking at this GWP Bio approach, which is more of a stand level approach, there's also another approach that's being discussed right now, and this is being discussed by some experts, but it's there's no consensus on whether or not this makes sense or whatnot. But I just wanted to present it here. There's this A0 upstream embodied carbon approach, which essentially tries to look at the landscape level. So let's say if I looked at a certain parcel of land, or even potentially the whole province, what is the change in the forest carbon stock within that geographical boundary? And then I divide that by what's the harvested timber from that year. And so that can give you some indication. This is just another way of quantifying the carbon fluxes in the forest in a way and mapping that. And so you can see this has been done in the States with EcoTrust. I think this is developed by David Diaz and others. So they've kind of modeled this at a more granular resolution of different parcels of land. And then they come up with a different kilogram of CO2 per meter cubed of roundwood. And, many of them can be on the negative side. Some parcels are on the positive side as well. But the reason why I bring this up is that if you think about on the provincial scale, when we look at our provincial GHG inventory, there are many different categories that are actually not included in our official GHG inventories. And that mainly pertains to what's called the other land use categories. So that includes things like wildfires, which are considered natural disturbances, right? So they remove it for a reason. There's also forest growth minus decay. So like, is the forest net sequestering carbon? There's slash burning emissions and decomposition of harvested wood products, which is the brown part. So you can see, from 1990 to 2019, there's big fluctuations, and the net emissions, which is these black lines, you can see in the previous, prior to 2000 or 2002, it's mostly a net sequestering, or like at least these emissions are negative. But then due to, for instance, things like the pine beetle and also the wildfires, lately they've been higher on this front. So if you stack those emissions, these gray bars, which are the other land use category that's not included in our inventory, and you stack that on top of the provincial GHG inventory, as you may recall, I said it was at 68 megatons of CO2 province-wide across all the sectors. But then you stack on things like the wildfires and whatnot, you can see these emissions can be very, very significant, right? And so the forest can be both our biggest carbon sinks and or our biggest carbon sources. And I think the forestry sector has a huge role to potentially to play in terms of addressing these emissions, right? Now we know that there's been a lot of major wildfires. 3 of the past 5 years have been record-breaking in terms of the wildfires. So you can see this is actually where those wildfires took place over the past 5 years. This is coming from the latest research from PICS, the Wildfire and Carbon Project. So Werner Kurtz is involved with this. And so there's some maps that are being produced which look at, what is the wildfire threat? So you can see a big chunk of the province is actually high to extreme wildfire threat. And so that means that there's a lot of potential for a lot more of this carbon in the forest to be susceptible to wildfires. And so we need to actually think about our forestry strategy and how can we actually reduce the risks on this front. And I think this is something that the forest sector can actually play a huge role in. This map just shows the stand age across the province. And then this shows the wildfires and the clear cuts as well. The dark lines of the timber harvestable land base area. So if you kind of overlay all 3 graphics, this just gives you kind of a sense of province-wide, where are the trees, how old are the trees, and where's the wildfire threat assessment on this front. So why am I bringing this up? Well, this could also potentially influence something like this A0 approach, right? So, previously, with the GWP bio approach, maybe we apply some multiplier with that amount of wood that's stored in the building product. But what if we were to also look at this kind of A0 landscape-based approach? So now I don't think that, first off, this is like a fairly new method. I don't really know if this is the right approach. I'm just kind of taking an initial stab at including various different elements just to see what would happen and how this would influence our assumptions. And I want to emphasize that none of these assumptions are necessarily the correct assumptions, or I'm not even saying that we should include wildfires or not, but I just wanted to show how significant our assumptions can influence the numbers or LCA modeling. So for example, I created one that was a limited scope where I just looked at deforestation and afforestation. These are included in our inventory. They're already accounted for. And then I also included forest growth minus decay. So in a limited scope, I just modeled that. And then in the full scope, I modeled slash burning, wildfires, and decomposition of harvested wood products. But for wildfires, I just attributed 10% associated with the A0. And then I created another scenario where it's 100% wildfire. I think in reality, it probably doesn't make sense to include 100% of the wildfires because there's definitely it is a natural disturbance. But it's useful to think like, if we include even a certain percentage of the wildfires in this, how would that influence these estimates? So I then took the GHG inventory. I computed the total volume of wood harvested each year. And then I divided that, I took the A0 emissions, and they're based on a 5-year rolling average. So it kind of smooths out some of the spikes. And so to show you like the results of that, you can see that this A0 factor changes because it's based on a 5-year rolling average. With limited scope, with full scope, with just 10% of the wildfire, that's this one. And then 100% of the wildfire, that's this dark blue line. So obviously a huge range, from limited scope being a negative number to, if we included some of those other categories, there would be a positive emission number. And so if you kind of rolled that into this A0 tool, this upstream tool, if you use that limited scope based on the 2019 5-year rolling average, that would be a negative 115 kilogram of CO2 per meter cubed. And in contrast, the A1 to A3 emissions for these wood products, the ones that we mainly focus on in our EPD is, for example, in this case, 124 kilogram of CO2 per meter cubed. But then if you use that full scope with 10% of the wildfire, then that brings that number up to 1,584 kilogram per meter cubed. And if you went 100% wildfire, which again, I don't think is a realistic or is a proper way of kind of attributing it, but that could be up to 3,700 kilograms of CO2 per meter cubed. So as you can see, this completely dwarfs some of the numbers that we're talking about here, right? Which makes intuitive sense. But the thing I want to end with is that, all models are wrong, but some are useful. You may have heard this quote before. It's attributed to George Box, who's a statistician. And in reality, we cannot come up with the perfect model to model our forests, or even to do our life cycle assessments to say that this is definitively the best representation of reality. Reality is always more complex, but some models are useful, and we do need to simplify. We do need to abstract. Now, what's oftentimes not or what people may not be familiar with this quote is the second part of this, where they say he says, not just all models are wrong, but some are useful, but also since all models are wrong, The scientists must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad. And what that's saying is that we need to worry selectively, right? We cannot put all these parameters, all the aspects of the forest into our model. It's not realistic to think that we can accurately model this to fully reflect reality. But we should also think about which parts of our model is importantly wrong. Are there blind spots in here? Are there things that we need to consider further? And so the take-home message with that biogenic carbon piece is not saying that GWP bio is the best approach or A0 or either of those approaches are appropriate at all. But there's a lot of active discussion happening on this front. Here are some resources. This was the presentation I did before. But also, I think the BC provincial government is commissioning Athena with James Salazar and Adam to develop kind of a survey on the current biogenic carbon landscape. So that report will be published soon, which will kind of dive into a bit more on this. And I don't feel very qualified to talk about the forest because that's not really my forte, but I'm trying my best to understand the information that is in there. So there's some summary slides here. You'll see the summaries in here, which summarize each section, but I'm already over time. So we'll go into Q&A. I know, unfortunately, this was quite a bit of content, I know, for everyone, but Caroline, are we okay to potentially stay on for a bit longer? I'm happy to stay on for as long. And this will be recorded, so people will be able to see the Q&A afterwards.